What specific problem does the proposed DeepSeek-R1 and its distillation method aim to address within the realm of model reasoning and performance?
The proposed DeepSeek-R1 and its distillation method aim to address the challenge of enhancing reasoning capabilities in smaller models while maintaining high performance levels. Specifically, the research demonstrates that reasoning patterns from larger models can be distilled into smaller models, resulting in superior performance compared to those trained solely through reinforcement learning (RL) on smaller architectures. The distillation process utilizes 800K samples curated with DeepSeek-R1 to fine-tune various open-source models, such as Qwen and Llama, thereby significantly improving their reasoning abilities. The evaluation results indicate that distilled models like DeepSeek-R1 Distill Qwen 32B achieve impressive scores on benchmarks, outperforming previous models and demonstrating the effectiveness of the distillation technique. Ultimately, this approach not only enhances the efficiency of smaller models, but also provides a pathway for the research community to develop better reasoning capabilities without the extensive computational resources typically required for large-scale RL training.
Can you describe how the proposed DeepSeek-R1 algorithm works? Please illustrate it step by step, including the key components involved in its architecture and training process.
The DeepSeek-R1 algorithm operates through a structured pipeline that enhances reasoning capabilities in models using reinforcement learning (RL) and cold start data. First, it begins with a cold start phase where a small amount of high-quality long chain of thought (COT) data is collected to fine-tune the base model, ensuring that the initial outputs are readable and coherent. This is followed by the application of RL, where the model is trained to optimize its reasoning abilities without relying on extensive supervised data, utilizing a rule-based reward system that evaluates accuracy and format. The architecture includes a self-evolution process, allowing the model to autonomously improve its reasoning through extended test time computation, which fosters sophisticated behaviors like reflection and alternative problem-solving strategies. Finally, the distilled outputs from DeepSeek-R1 are used to fine-tune smaller models, demonstrating that even compact architectures can achieve competitive performance by leveraging the reasoning capabilities distilled from larger models.
Could you provide a simple yet illustrative example that demonstrates the inner workings of DeepSeek-R1, particularly focusing on how the reasoning capabilities are improved through the proposed methods?
DeepSeek-R1 enhances reasoning capabilities primarily through a two-step process involving reinforcement learning (RL) and the use of cold start data. For instance, in the training of DeepSeek-R1 0, the model begins with no supervised fine-tuning and learns to solve complex reasoning tasks purely through RL, achieving a significant performance increase on the AMY 2024 benchmark from 15.6% to 71.0%. This improvement is further augmented by majority voting, which boosts the score to 86.7%. In contrast, DeepSeek-R1 incorporates a small amount of high-quality cold start data, which helps stabilize the initial training phase and results in more readable outputs. By distilling the reasoning capabilities from DeepSeek-R1 into smaller models, such as DeepSeek-R1 Distill Qwen 7B, we observe that these distilled models can achieve competitive performance on various benchmarks, demonstrating the effectiveness of the distillation method in enhancing reasoning abilities.
What are the theoretical or practical advantages of using DeepSeek-R1 over previous models, such as DeepSeek v3 and OpenAI models, in the context of reasoning tasks and overall performance?
DeepSeek-R1 demonstrates significant theoretical and practical advantages over previous models like DeepSeek v3 and OpenAI models in reasoning tasks and overall performance. Firstly, it achieves superior scores on various benchmarks, such as 79.8% pass at 1 on AMY 2024 and 97.3% on Math 500, outperforming DeepSeek v3 and showing competitive performance against OpenAI 12.17. The model's reasoning capabilities are enhanced through large-scale reinforcement learning (RL) without relying heavily on supervised data, allowing it to autonomously develop sophisticated problem-solving strategies, as evidenced by its self-evolution process. Additionally, DeepSeek-R1 excels in handling long context tasks and demonstrates strong performance in creative writing and general question answering, achieving an 87.6% win rate on AlpacaVal 2.0. Finally, the distillation of DeepSeek-R1 into smaller models, such as DeepSeek-R1 Distill Quen 32b, results in efficient models that significantly outperform non-reasoning models, showcasing the effectiveness of the distillation technique in enhancing reasoning capabilities.
How was DeepSeek-R1 tested and validated, specifically detailing the datasets used, the metrics for performance evaluation, and how these measures reflect the effectiveness of the model?
DeepSeek-R1 was tested and validated using a comprehensive set of benchmarks, including MMLU, MMLU Redux, MMLU Pro, CEval, CMMLU, IFEval, Frames, GPQA Diamond, Simple QA, and others with specific focus on educational and reasoning tasks. Performance evaluation metrics included pass-at-1 scores, consensus results from majority voting, and win rates on various coding and creative writing tasks, such as those on Codeforces and AlpacaVal 2.0. For instance, DeepSeek-R1 achieved a pass-at-1 score of 79.8% on AMY 2024 and excelled in math tasks with a score of 97.3% on Math 500, indicating its strong reasoning capabilities. The model's outputs were also assessed for readability and coherence, particularly in the context of long context understanding, where it significantly outperformed previous models like DeepSeek v3. These measures collectively reflect DeepSeek-R1's effectiveness in handling complex reasoning tasks and its competitive edge over other models in both educational and coding benchmarks.
What limitations or drawbacks did the authors acknowledge regarding DeepSeek-R1, and how do these limitations impact its application or future development?
The authors acknowledged several limitations of DeepSeek-R1, including its tendency to produce poor readability and issues with language mixing, which can hinder user comprehension and practical application. Additionally, while DeepSeek-R1 demonstrates strong reasoning capabilities, it struggles with certain queries due to safety reinforcement learning, leading to a refusal to answer some questions, particularly in the Chinese Simple QA benchmark. These limitations impact its application by potentially reducing user trust and effectiveness in real-world scenarios, especially in educational contexts where clarity is crucial. Furthermore, the authors noted that the engineering performance of DeepSeek-R1 is currently limited due to a lack of sufficient related reinforcement learning training data, suggesting that future development will need to focus on enhancing this aspect to improve its overall utility. Overall, these drawbacks highlight the need for ongoing refinement and the incorporation of more user-friendly features in future iterations of the model.